So we call the system as multi-stage refrigeration system because it involves more than one. Some of the components involve more than single unit. And what are those components that might involve uh, more than one? So we can have one compressor and then two evaporators. We can also have two compressors and one evaporator, as what we have discussed before. I think it was also given in the midterm exam. Now we have two compressors, meaning two-stage compression system, but we have only one evaporator. But there is an intermediate heat exchanger somewhere in the middle. That's why we were able to get the intermediate pressure. So that was before, two compressors, one evaporator. But now we are going to deal with the two evaporators and one compressor, no, for that matter. So let me go straight to our problem, which is we have started last week or last time, no, last meeting. We will just have a review, and then we will continue with the other problems. Okay, so this is the problem, and I think it was given to you last time, no? So calculate the power required by a system of one compressor serving two evaporators. One evaporator carries a load of 35 kilowatts at 10 degrees centigrade, and another is 70 kilowatts at negative 5 degrees centigrade. A back pressure valve reduces the pressure in the 10 degrees centigrade evaporator to that of the negative 5 degrees evaporator. The condensing temperature is 37 degrees centigrade, and the refrigerant is ammonia. Now the question is, or the required, or what is being asked of us is the coefficient of performance. So the question is, what is the coefficient of performance? So now I guess we have to have a systematic approach in this particular problem. Okay, so first what we are going to do is we lay down, no, we lay down all the given or all the known data, all the available data that is given to us, no? So I might write the given in the space available. So let me get a pen. So let me have this now. So we write down the given as it appears in the problem. Now, so now first calculate the power required. Now, so at first we are being asked of the requirement. Now, what is the power? Yeah. So here, if I may write here, so we are being asked of the power, right? Power, right? No? Um, and then the COP, no, and the coefficient of performance. So if I may highlight that portion, no. So first we are asked of the power, no. So power, and then here at the last part is the coefficient of performance. We go to the given one compressor. So we have here. I just write it down here now so that we can see side by side or at the same page the given and the figure. So what is given to us is one compressor and two evaporators. Two evaporators. Okay, so here, one compressor serving two evaporators. No, one evaporator carries a load of 35 kilowatt at 10 degrees centigrade. No, so say let us jot down the given evaporator. Let us say evaporator 1, no, because that's the first evaporator mentioned according to chronological order. So here is 35 kilowatts, and the temperature involved is 10 degrees centigrade. No, then the other evaporator is what? So we may call the next evaporator or the other evaporator as evaporator 2, and the load is what? 70 kilowatts, and the operating temperature is -5. Yeah. What else? It says there that a back pressure valve reduces the pressure in the 10 degrees centigrade evaporator to that of the -5 evaporator. It only says that the evaporator or the second evaporator was reduced in pressure because of the back pressure valve. So meaning the second evaporator is a much lesser pressure and temperature. Yeah. So from 10 degrees to -5. No, when we lower the temperature, of course the pressure follows. Not the pressure follows. So meaning that the evaporator 2 has lower temperature and pressure also. Okay, so we will explain that a bit later in the pH diagram. Now, moving on with the given, also given is the condensing temperature. Now, so I may put here in the blank part of the slide, which is somewhere on the left. Now, so the condensing temperature is what? 37. Now, so 37. So meaning let us say TC, no, or TCO, yeah, just to be descriptive. So the condensing temperature is 37, right? 37 degrees centigrade. So condensing, then evaporating temperature, because we have two evaporators. Now, the best way to illustrate the problem is by the use of pH diagram, right? So below is the pH diagram of the problem. So we are going to explain this one by one. First, we have to label this. Right? So pH, no? P is in the vertical and H is in the horizontal. So P stands for pressure and H is enthalpy. And that is the famous or the most common diagram being used in the refrigeration system. The other is TS, no? But but it is more convenient. It is more handy to use the pressure enthalpy diagram. Yeah. TS is more on the power plant. For example, steam power plant, we always use TS diagram, meaning temperature entropy. So now this is the pH diagram as what we are discussing. Now, before we continue, let me explain the parts of the pH as it relates to the problem. Now, first we were given the evaporator, and then we have two evaporators. I believe the next question is, where is the evaporator in the pH diagram? Now, so it's a diagram, it's just a line and curve, but it is more than that actually, because it represents the components of the refrigeration system. So now I would like to it will be more clear to all of us. So evaporator 1, no, it is given the temperature. The temperature is 10, yeah, 10, and the other is -5. So the question is, where is this evaporator 1 and evaporator 2, no? So logically, the evaporator 1 is at the higher temperature and higher pressure. We were only given two pressures there, and I mean two temperatures, no? So 10 and -5. The higher pressure, the higher temperature. The lower the pressure, the lower the temperature. So we can infer, we can deduct, no? We can say that the -5 is here, right here, because it is lower temperature, lower pressure, right? So let me put here. Now we will use the right side because it is already numbered, and I will explain the numbering now. So this is the P, and this is the H, right? So this is the H, this is the P. So now I will put this label as evaporator 2, no, because 2 is -5. Now as you can see here, 2, -5. Then evaporator 1 is what? Evaporator 1 is this with a 10 degrees centigrade. So this is the evaporator 1. Okay? So meaning the evaporator 1 is happening in this line. No? So this one from 4 to 5. Yeah, this one. Because it's already numbered, no? So process 4 to 5 is happening in evaporator 1, and process 7.1 or 1.7 is happening in evaporator 2 because it has lower temperature, so -5. The other evaporator is what? 10 degrees centigrade. Okay, so I think we are clear with that. Now, the other given is what? The condenser. Now, the condenser is 37. Look at this, yeah? So here, 37. Now, a much higher temperature compared to the evaporator. So this is our condenser, right? So we have evaporators because there are two. We have condenser. What about the other two major, other two major parts? We have the compressor. So this line, as you can see, the curved line. Let me use the left side so that it will not be a bit crowded. No, so this one, no. So this line here, if everybody sees this is the process that relates to the compressor, no. So this is the evaporator at the bottom. Why bottom? Because it has lower pressure, and if you have lower pressure, lower temperature. In this case, we have two evaporator. Now the higher side, this process here, this line is the line that has to do with the condenser. What about this vertical? So this vertical line on the left is what? It's the metering device, meaning it is regulating device. The general term is metering device, but the engineering term is this, no? TEV or EV or TXV, no? So different people, different lands, different literatures are using, but TEV stands for thermal or thermo expansion valve. EV is expansion valve, no? And TXV is thermo expansion valve. So all these are just one and the same. So what it does is it lowers the pressure. No, that's why it's called thermo static expansion valve, meaning the temperature and the pressure are related, no. So once you lower or you change the pressure, once you change the pressure, you will it will have a corresponding change in temperature. Or once the temperature is changed, then the pressure of the refrigerant will be changed. Meaning, there's a sensor. No? There is a sensor at the in front at the front of the evaporator. There's a sensor. There's a bulb. No, there's a bulb there. No, so but not valve but bulb. No. So for example, this is your evaporator in your aircon. For example, in your room, right? The one in front is the evaporator, and the one at the back is the condenser. It removes heat, QR, but here is heat is absorbed. No, so the hot air is absorbed in the room. But if you open the window or box type, there is this kind of thing, bulb, no? But yung bulbilla, no? A bulb like bulb, no? Like a thing sensor, yeah. So once it receives temperature, it will register. Then it will change the opening of the expansion valve to allow the proper amount of refrigerant going to the evaporator at a lower pressure. So as you can see here, if I'm explain, from here it is still liquid, right? So this is saturated liquid line. So meaning F, no? F line here. So it is still liquid, but here is still high pressure. How can I say it's high pressure here, right? So this line is high pressure. But when it goes to the evaporator, so meaning it is the pressure, what happens to the pressure? The pressure is going down. Why is it going down? Because of this process is being administered or done by the thermal expansion valve. So when it registers some kind of temperature from the room, then it will correspondingly change the opening of the valve, meaning the opening of the valve ball, the ball valve. Okay, so there's a spring there, there's a bulb, there's a valve head and everything, there's a balancer and everything. Now so you see the process here is what? Constant enthalpy. Now because here is enthalpy, and if you see a straight line, meaning it is behaving in constant enthalpy. We call that isenthalpic, no? Isenthalpic process. Okay, so we are I guess we are clear with that now. So we already labeled the parts of the vapor compression system as it relates to the pH diagram. So now how do we do the number in a systematic way? So look at this. Now, so one, normally we start one with the heart of the system. Now, heart means that is the most critical part of the system where compression is done, where work of compression, the power of compressing is done. So that this is the compressor, right? So this is the compressor. So we label that as one, right? Then two, end of the compression system. Then from two to three, what is happening there in two to three? That is the condenser, right? Condenser. So what is happening in the condenser actually is it has kind of a superheat region, right? Yeah. So at the discharge, this is the discharge of the compressor. The end of the compressor is the discharge, and it has a state, no? State meaning condition of superheat, no? So I'll abbreviate that as SH, which is superheat. Yeah. So from 2 up to this point, let me put this, let us say 2 prime, no? So from 2 to 2 prime, there's a condition here which is superheat. What is superheat? It is the region where it is above saturation. But from 2 to 2 prime, it is superheat. So we have to remove the superheat. Now, when you remove, meaning you lessen the energy. No, you lessen the heat energy. That's why going to the left, you reduce the enthalpy, right? Because this enthalpy line. So when you go backward to the left, you are reducing enthalpy, so you are de-superheating. The prefix is the superheat. Yeah. So when you remove the superheat, and then when you reach this, when you reach this 2 prime here, that is saturated vapor. That's why the the condition here that you will get is all about gases or vapor. No? So here you can have the entropy of gas, yeah, volume of gas or specific volume of gas. Now the refrigerant is gas, gaseous state, no vapor state, and enthalpy of gas. Now enthalpy of gas, specific volume of gas, entropy of gas, and the other. Yeah. So here is gaseous state. So when it goes down, enthalpy is reduced. It will go to this 3. And what is 3? This is saturated liquid line. Now, so let me be clear to you. This is saturated liquid line, right? So let me remind you. No, it's a basic. Once you go to the half, no, of the dome, that is a dome curve, no dome. Yeah. So it is a bell or dome, yeah, bell, like a bell curve. So it is a bell curve leaning to the right, now somewhere to the right. So this half left, as a review, this is uh, half left that is a saturated liquid, so F. Then here, from here up to this, all those points that is coinciding with the line, you will get vapor. What kind of vapor? Saturated. And it's a lot easier to get the data from the pH diagram on the table or on the chart, no? Because it is saturated. Now, saturated vapor on the right side, saturated liquid on the left side. So how do we numbering? So it's kind of counterclockwise. No? So counterclockwise meaning opposite of the direction of the clock. So meaning counterclockwise for the numbering is like this, right? Yeah. So anti-clockwise or counterclockwise. So 1 to 2, that is the compressor. 2 to 3, that is the condenser. So yeah, here. Then 3, 4, and 7, what is happening in 3, 4, 7? So what is the device there? 347 is about expansion valve. So 347 is expansion valve, constant enthalpy. So if you're gonna look at the vertical part, it is constant, meaning straight line. The pressure is lowering. Look at this. If I may illustrate to you, so this liquid line, this is the liquid line. From the liquid line, it goes down. What is going down? The pressure, right? So the pressure is going down, but the enthalpy is fixed. Now, for example, somewhere here, no. So that property, I mean the enthalpy reading is fixed here, but the pressure is going down. Pressure is going down up to the entrance of the evaporator, which is 7, right? 7 is the entrance of the evaporator 2. Evaporator 1 entrance or entry point is 4. Okay? So 2, 3, 4, then 5. No, let me get so 2, we have 2 already, then 3, then 4. You don't go directly to 7, no, because this is the evaporator, so it has to process the evaporation in the first evaporator. Yeah, 4, 5, then we have 6 here. No, we have 6, the numbering. Then 7, here is the 7, then another evaporator, then it goes here to the 8. Okay, so that is the explanation for the pH diagram of this problem before we solve this systematically. Now we go to the required, and that is the power. So the power is required and the COP, and let me go to that. Yeah, so power. Okay, let me put here so that we are clear now before we solve this, right? So here, the required, if I may write it down. So A is the power. Where is the power happening? Power of compression or work, no? So because work over time is power, right? There's only one device or equipment that involves work there, work. Now when we tag the label work, now there are only devices that is doing the work. For example, in refrigeration system, what is that device that does the work? Compressor. Yeah, so compressor. So if you have that, now work of compressor is, if you go back here, what are the involved? 2 and 1. Process 2 and 1. So 2 is the discharge point of the compressor and 1 is the suction point of the compressor. So 2 is obviously higher, no? The energy at 2 is higher. Higher temperature, higher pressure. 1, lower pressure, lower temperature. As you can see this, it's -5 only, no? So from here, the formula is this, no? So M delta H, the general formula is M delta H, which is mass, no? Mass 1. Now, if you will see there, because 1 to 2, no? So let us say mass 1, then the involved enthalpy is H2 minus H1. You see? So here, there's a mass flow of refrigerant here at 1. Here, yeah? So there's a mass flow. The refrigerant has to enter the suction valve, the suction port of the compressor, and it will be compressed until it reaches 2 at a superheat region. So the one involving the work of compression is 2 and 1. So 2 is higher, it's a positive, no? H2 minus H1 times mass, and that's going to give us work of compression. So we can check the unit, no? So that before we compute, we will be so clear about this. No? So units check. Okay. So what is the unit for the mass flow? It's in kilogram per unit time, per second, or per hour. Let us use the second as the standard unit for metric system. Then the enthalpy, because H2 minus H1 is just the same unit, right? Same enthalpy. The unit for the enthalpy is what? Kilojoule per kilogram. So what's going to happen in this equation? Kilogram and kilogram will be cancelled, right? And what will remain is kilojoule per second. And we know that in thermodynamics or engineering conversion system, when we have this kilojoule per second, we are going to get kilowatts. Okay, kilo, the prefix kilowatts, no? Because joule per second is watt. Then we just retain the K or kilowatt. Now, so we're clear with that. Now, if I may put here the B, we are asked of the COP. What is COP? Coefficient of performance. And what is coefficient of performance? The coefficient of performance is just the heat load, no, of the evaporator. Now, meaning heat at or load at evaporator, meaning the heat, the total amount of heat that the evaporator has to absorb from the divided by the work. This one, work of compression. Okay, so in this case because we have two evaporator, so meaning the the heat load at the evaporator is called RE, or refrigerating effect. So let me have this RE, meaning refrigerating effect. Why refrigerating effect? Because the cooling is happening in the evaporator. Refrigerating effect, no? So in this case, COP is refrigerating effect of evaporator 1 plus refrigerating effect of evaporator 2 divided by work of compression. So that is our formula. Okay? And then the formula for work of compression or power is this. Okay? So we have this one and we have this two as our major or principal equation, mother equation, if we may say that way. Okay, so we continue. So only here at the slide, we were given the known data. Okay, so here it is given in the notation Q10 is 35 kilowatts. And what is Q10? Here, the first compressor, right? You see this 10 degrees centigrade, and the heat there is 35 kilowatts, meaning heat load, right? So here, I'll just put some annotation here, right? So this is the given, given in the very big bold letters. So this is the Q10, meaning heat load at 10, meaning 10 degrees centigrade. Now, so this is the temperature. Temperature of evaporator 1, right? Q is the heat. Q is the universal notation for heat, no? Heat load, meaning the amount of heat that the evaporator should absorb, it should get that amount of heat, no? So it was given 35 kilowatt, no? So 35 kilowatt, and the temperature is 10. That's why it's Q10. No, it should be a subscript. No, it should be a subscript like this. No, Q10, right? So 35 kilowatts. Now there is another Q, which is Q, or the heat to be absorbed at the evaporator at a temperature of -5. That's why Q -5. This one, yeah? Q -5, and that heat load at that evaporator is what? 70 kilowatts. Yeah. So here. So now, what is the operating temperature at that evaporator? -5. Now it should be lower. Why? Because it is, yeah, as you can see in the diagram, it is below evaporator 1, which is 10. And the reason why it is -5 is there is this device. What is that device? A back pressure valve. If you read this properly or carefully, a back pressure valve reduces the pressure in the 10 degrees centigrade evaporator to that of the -5 evaporator. That's why the pressure went down, and if the pressure goes down, the temperature also will go down according to ideal gas law, no, by theory. So from 10 to -5. Now, I think we're clear with that. Now, the next step would be here. Now, the next step would be we find. No? So next step is find the uh, the necessary or needed necessary properties, meaning the ones involved. So in the formula, we go back to the formula. What are the properties that we are going to find here? Delta H, no? So enthalpy, RE. So what is the formula for the refrigerating effect? Refrigerating effect is only the difference between the higher enthalpy energy minus the lower enthalpy energy. So here, now refrigerating effect 1, refrigerating effect 2. Let me show you how to get the formula. So refrigerating effect 1, here at the happening in the evaporator 1. Look at this. Here, no? So refrigerating effect involves 0.5 and 4. 0.5 and 4. So let me clear that, right? So the refrigerating effect at evaporator 1 is this, no? 5 and 4. Enthalpy only. Yeah, look, this one and this one. So it involves 5 and 4. So here, if I may write enthalpy, which is higher, enthalpy 5 minus enthalpy 4. There should be a mass. Now, so the mass flow coming here No, we will designate that later. No, we will have a designation of that. Is on the evaporator one, we can have that refrigerating effect one. Now, the refrigerating effect of the second evaporator is this, no? Refrigerating effect of evaporator 2, no? Or refrigerating effect of 2, no? That's the second refrigerating effect. There's no other, no, except that, no? So the refrigerating effect is this. Now, what is the involved? Sorry. Here, right? Yeah. 8 and 7. So H8, which is higher energy, now because it's going to the right, now then the lower is 7. So here, this point and this point, so there's a quantity or distance, no, from point to point. So H8 is higher than H7. So if you multiply that with the mass going into this suction, no, at the entry of the evaporator, you will get the mass flow rate of the refrigerant. And what is that refrigerant? I guess it is ammonia. Yeah, ammonia, I guess, the one used here. So H8 minus H7. So that is refrigerator. So my point here is what are we going to get from our tables, from our charts? It's only the enthalpy. It is only the enthalpy here, enthalpy. No? So we are expected to know the different enthalpies, okay? And then we will discuss that here one by one. So we don't need entropy, we don't need specific volume at this problem. We only need enthalpy. Now, how do we read the enthalpy? That is the next question. So let me go back to the chart. Yeah. So look at this. No. So look at this. I will clear this. No. What can we say about the enthalpy? So first, the enthalpy involved in the power, because the power is the one needed. The enthalpies involved in the calculation of the power of the compressor, now where work is done, is this 2 and 1. Now, 2 and 1. Now, so we should be able to get from the chart the enthalpy 2 and enthalpy 1. And how do we get that? As you can see here is this region is beyond, no, the saturation line. So this is the saturation line. This I think it's green. I'm a color blind, but this dark line here is saturation. Beyond saturation line is superheated region. Now, so you get the superheat here, and then here is the one. Now, so we can get that. The other is the enthalpies at the different points, right? For example, we are going to get the H4 and H5. Look at this now. We have to get the H4 and H5, right? Why? Because we need to calculate the refrigerating effect at evaporator 1. The first evaporator is here at 10 degree centigrade temperature, and the evaporator 2 is at -5, no? -5 temperature. So we get the enthalpy 7 and enthalpy 8, no? Now, I want to teach you, or I want to remind you of the technique, how to get easily the enthalpies, no? Because it seems like when you draw the following data, or the given data in the pH diagram, it appears like a complicated system, but the technique here, the technique here is this, no? So we have to be very systematic. Now I will use another. Yeah. So here there are enthalpies that we can easily get from the chart, right? So look at this. We may first look into this point 3. Wait, sorry. So this point 3 here, class, where is this point 3 located? it is located exactly, no? It is exactly located or situated in the line, no? Along the line or on the line, no? Along the line. So meaning it is what? Saturated liquid. Saturated liquid line, right? So here, saturated liquid, easily you can get the HF, enthalpy of fluid, because it's a fluid. Now, if I ask you, is there a quality there? Quality of refrigerant. Quality is X. Another term for quality is dryness fraction. So is there a dryness here? What is a dryness here? What is the value of dryness here? The value of dryness here is X equals 0. Why 0? Why 0? Because it's not dry. It's fluid. It's liquid. So 0%, because you don't have any percent of dryness. No, it's 0, right? So all you can get is enthalpy of fluid. Now, the enthalpy of fluid at 3, no, going down is the same, no? At 4, going down 7, right? Because it's in vertical line, and it is the enthalpy, as you can see, diba? H. So here, so all this value here is the same. So we can say that enthalpy at 3, enthalpy at 4 equals enthalpy at 7. No? So 3, 4, 7 is just the same value. So immediately you have three values of enthalpy. Enthalpy 3, enthalpy 4, and enthalpy 7. And how do you get the enthalpy at 3? You should get the enthalpy by knowing the other parameters. So here, the known parameter is the condensing temperature, like 37, right? At here. So go to the chart. You find the saturated temperature 37, right? So at Tsat, Tsat, saturated temperature 37 degrees centigrade, all the other values will be given. The enthalpy, the entropy, the volume, and the others. So you can get from temperature saturated 37 degrees centigrade, you will get the HF. I think we're clear now. Once you get the HF at that point of 37, which is H3, it's just the same with H4, the same with the H7, because it's in vertical line. What is the other enthalpy that you can get? The other enthalpy that you can get is H5. Now, H5. Look at this H5 class. Look at this H5. Where is this situated? The 0.5, the 0.5. You see this? 4, 5. By the way, what is 0.5? 0.5 is what? The discharge of evaporator number 1. Yeah. So evaporator 1, evaporator 2, condenser. There's only one condenser, right? This is the compressor. So this one is the compressor, right? Okay. So point number 5, I want you to focus on number point 5. The point 5 is this, right? The point 5 is the discharge of this evaporator. So there's an evaporator process here, 5 and 4, or 4 and 5. This is the discharge. This is the suction port. Yeah? The one, entering. The refrigerant enters at 4, discharge at 5. So at point 5, there is this saturated vapor. So this region I told you is vapor line, vapor. So the notation used is G. So you can get the Hg, enthalpy of G, meaning vapor, gas, because the vapor is gas, right? Gaseous state, gaseous state. Now, so 5. So 5 is the same as 6, no? So here is the 6, no? So there's a 6 here. It's in vertical line, right? So easily you can get the H5, which is equal to H6. So 1 is here, 2, easily we get this. What's the other one? 3, right? So is everything clear about the evaporator one? All you have to do is to get the enthalpy at what parameter? 10, not 10 degrees. Okay? So meaning Tsat. So this portion here, Tsat is based on 10 degree centigrade or 10 degrees Celsius. Look at this, right? Look at this, yeah, 10. So all this is 10 degrees centigrade, not 10 because there's a constant temperature line. So here, look at this. So there's a temperature line here, constant here, then here, right? Here is 37. It goes here, then here. 37 degrees centigrade. This is 10 degrees centigrade. Then here, constant temperature line. It goes straight, constant temperature. Then here. So this is negative 5. Negative 5, right? Negative 5 at evaporator 2. Okay? So all you have to do is to get the Tsat in this process. What is the T saturated saturation temperature? 10. So 10 degrees centigrade, look at the pressure, right? So there in the table or table, you can get the saturation temperature 10 degrees centigrade. All will be given. The pressure will be given, the enthalpy of gas at 10 degrees centigrade will be given, the specific volume will be given, the entropy will be given. Okay, so we have explained the second enthalpy that is kind of easily to get. No? So as a recap, we can get the H3, right? Same as H4, H5. We can get H5, H7. We can get the H5, which is equal to H6. Now, the other enthalpy that we can easily get by referring to parameters is this, no? The 2. And the question is, what is enthalpy 2? And how do you get the enthalpy 2? How do you get the enthalpy 2? Okay, so you can get the enthalpy 2. Now here is the 2 beyond the saturation line. That's why we call this superheated, no, superheat region beyond. That is beyond this line of saturation. We can get that from here. One. Now look at this one. 1 and 2. See, you see here 1 to 2. What is the equipment involved? The equipment involved is compressor. And what is the process involved? Isentropic. Isentropic means entropy is constant. Now, so if you get the one here, then you project there, you can get the 2 because this is constant entropy line. I'll repeat, constant entropy line. Yeah, so constant entropy line. So here you get the entropy. Once you get the entropy at negative, it's supposed to be negative. You get the entropy at saturated temperature of -5. Then if you have the entropy, you project that because those are the entropy lines, entropy lines. So here at point 2, you have the entropy, right? So there's a value of entropy and then there's a value of saturation temperature, which is 37. Okay, so meaning at temperature of 37 degrees centigrade and what? entropy of this value, which is coming from 1, you can get the enthalpy 2, no? Enthalpy 2. Or otherwise, we can get this by mass and energy balance. Mass and energy balance, no? So, but my point here is the enthalpy 2, no? Enthalpy 2, we can get that easily because in the chart, there is this superheat region, right? The H2. We can get that. Once you get the entropy, you project because this is a constant entropy, and then once it reach the other parameters, which is 37 degrees saturated temperature, which has a pressure saturation of 1431.5, no? Because once you get the saturation temperature, you will get the saturation pressure. So this is just constant pressure because it is on the horizontal. Now P, look at this, P is constant. Now, so constant pressure, 37 degrees centigrade, going there. We have the constant pressure, 1431.5, and we have this constant entropy. Yeah, the point, the meeting point, now where they meet, then you can project downward. Just project downward. When you project, pardon for my line, so you project downward, then this entropy, you can have a reading here, right? So that's my point. So let us now look, let us see the values. Now, as I told you, H3, H4, and H7 is the same. Look at this. H3, H4, and H7. So let us go back here. Let me clear this up. Yeah. So here, H3, H4, H7 is constant. Why? Because they are lying on the same vertical line, and this is the horizontal line for the enthalpy. So only this value. So this value is only one. It represents H3, H4, and H7. So what is that value of H3 and H4 and H7? Here, 375.9 kilojoule per kilogram at 37 degree centigrade, no, saturation temperature. So look at this, right? 37 degrees centigrade, then this is the meeting point at saturated liquid line, sat liquid line, then you can get the 3. Now we're clear with that. Now, what are the other what are the others? What are the other enthalpy that we have to get? H5, H6, and Hg. So look at this now. H5, H6, and Hg. As I told you, that is located or situated in the saturated vapor line. So let me clear this up. Look at this now. So this 5 is Hg. Why? Because it is located at the saturated vapor line. Vapor means gas. Now vapor means gas. That's why G. Yeah. So the Hg here is the same as H6 now because it's vertical, right? How do we get that? We can get that with this 10. Look at the table. There's a 10 degrees saturated temperature for ammonia. Whatever is the refrigerant. Yeah, for example, ammonia. So if the refrigerant is ammonia, you go to the table and then look for the saturation temperature of ammonia refrigerant at 10 degree centigrade, and that will give you Hg. Now enthalpy of gas is the same as H6. So let me go back to our values now. So as I told you, H5 is saturated vapor line, same as H6, same as Hg. No, so this Hg is the one you can see at the table. You cannot see table H5, H6, no, because we are the only one who defines the numbering. No, H5, H6 we define, but in the table, the standard table and the references Hg. What Hg? Hg at 10 degrees centigrade. Now Hg at 10 degrees centigrade, we can get this. Okay. Now, what's the other? As I told you, we can have immediately the 3 enthalpies. Now, the other is H8. Now, it's H8. Here, yeah? So here is the H8. What is the H8, by the way? So evaporator 1, evaporator 2, suction of the evaporator 1, discharge port or point of evaporator 2. No? So 1, 2. So 7 and 8 is the process at evaporator number 2. Entry point or suction is 7. Discharge, no? Discharge or output is 8. Where is 8 located? Again, I ask you, where is 8 located? Fluid or gas? Of course, gas, not G. Here. So this point is gas. Okay? So Hg, you can get Hg at -5 degrees centigrade. You can get also the pressure, no? So 356 kilopascal. So you go to the pressure, you can get the enthalpy, or you go to the temperature, you can get the pressure, no? So saturated temperature -5, it will give you the saturated pressure, meaning the constant pressure here, the the constant pressure at that bottom process. Yeah, so the constant pressure at the bottom process here, right? Constant pressure, then you will touch that point at the vapor line, so it will give you enthalpy of gas at -5 degrees centigrade and 356 kilopascal. No, so easily you can get the H8. So I think we're clear with that. No, we were able to secure the values of H3. Okay, the enthalpy of gas. Then this one, enthalpy of fluid, sorry, enthalpy of fluid, then enthalpy of gas, then another enthalpy of gas. Okay, so we were able to get all those, and those are the values, right? So these are the values. Now we go now to the calculation. As I told you, we have to get the mass flow so that we can get the the power. No, we can get the power because we have to multiply the mass flow with the enthalpies involved. So here the calculation is like this. We isolate the evaporator 1, which is 10 degrees centigrade. So at 10 degrees centigrade, we can get the load, no, by multiplying the mass times refrigerating effect. Now, what is the mass entering to evaporator number 1? So the evaporator number 1 has a temperature of 10 degrees centigrade. Look at this, right? So here, evaporator 1, 10 degrees centigrade. What is the mass? Can you tell me what is the mass entering? What designation? This one, right? Mass 4 at evaporator 1. What is the mass entering at evaporator 2? Yeah, this is 2. This is 7. So mass 7. Why do we need that? Because we are going to calculate for the refrigerating effect. Yeah, refrigerating effect later. So we need to have this mass of refrigerant entering to the evaporator. So let us immediately go back to this, right? So here, the heat load, no, at the evaporator 10 degrees centigrade is MRE. Then the M, as I explained, as I explained, is M4. Now look at this, M4, the mass of refrigerant coming into evaporator 1, which is at 10 degrees centigrade, is this MRE. What are the enthalpies involved? You can see here H5 and H4. This one, H5, H4. Then the mass flow is M4. So it follows here, the formula is M4, H5, and H4. Now, the question is, do we have the heat load at the evaporator 1? Yes or no? Yes. Look at this. The problem says 35 kilowatts at 10 degrees centigrade. No? So the evaporator operating at 10 degrees centigrade has a load or heat load of 35 kilowatts, no? Or cooling load, meaning the amount of heat that it's going to absorb is 35 kilowatts. So here, if I may put here, no, so 35 kilowatts is given. M4, that is what we're going to find. H5 and H4, it's given now. H5 and H4 is given. We already got that, right? H5, here. We have H5, we have H4. Okay? So only we can find is the M4, mass flow at the entrance of the evaporator 1, which is at 10 degrees centigrade. So just plug in substituting values. 35 kilowatt is just 35 kilojoule per second. Now we convert kilowatt into kilojoule per second so that we can cancel the other parameters or units. Now, so substituting values, immediately we have this M4. Okay, same is true. Same process we have to do in second, no? Second evaporator. The second evaporator is operating at a much lower temperature, which is, according to the problem, -5 degree centigrade. This one, at -5 degrees centigrade, we were given a heat load, no, the amount of heat that the evaporator should, by design, absorb. No, it should absorb how many kilowatts? Let me go back to the problem so that we can see. At evaporator -5, it should have a 70 kilowatts load. No? So 70 kilowatts load. No? So all we have to do is to substitute 70 kilowatts here. This M7 is what? That's the mass flow rate entering the evaporator 2. Look at this. No? So let me clear this up. Okay. This is evaporator number 2. The entrance is 7. No? So our mass appropriately, no, should be designated as M7. So this is the suction. This is the discharge at the saturated vapor, no, discharge of the evaporator, which is the entrance of the compressor also. Okay. So going back to this, all we have to do is to plug in. We are going to find M7 at the second evaporator at the -5 degree centigrade. H8, we were able to get that because it is in the vapor line. And H7, we were able to get that because it is at the constant line. So look at this. So yeah, H8 is the Hg at -5. Now, then we have, what's the other? The other is this one, H7. Huh? H8 minus H7 for evaporator 2. Do we have H7? Yes, here. No, because it's the same as H3 and H4 and H7. It's a constant enthalpy, no, because of the expansion valve. So all we have to do is to plug in. Easily we can get the M7. That is the mass entering, the mass flow rate of refrigerant entering the suction of the evaporator number 2, which is at -5. Yeah? So we can get the M7, M4. Why do we need that? Because we will have the so-called mass balance according to first law of the thermodynamics, right? So mass entering, mass leaving, energy entering, energy leaving, energy in, energy out. First law of thermodynamics. So when you add M4 and M7, that is M1. So look at this, right? So look at this. Where is this? I think here, right? So here. So this, the mass 7, no? So the mass 7 is here. So the mass 7 is here, same mass, no? Law of conservation of mass, same mass here. That is the evaporator number 2. And then M4 is at evaporator number 1, no? So when you reach the end of the evaporator, so it will go to the compressor, right? According to our problem. So here is the evaporator. Let me just um, illustrate. So evaporator, this is the expansion valve. At a lower pressure, then evaporates. The liquid should evaporate because the compressor only needs a gaseous state. You cannot put a liquid in the compressor. It will explode. No, it will damage the crankcase and everything. No, it doesn't need a liquid here. Compressor needs gas or vapor only. So evaporator, after the evaporator, it will go to the compressor. And here, there's a meeting point of M4 and M7. Look at this. Now, M4 no, and M7. So let me illustrate that here in our diagram. No, so where is that? Here, M4, look at the mass. No, the mass entering at the first evaporator is this. The mass entering at the second evaporator is this. No, then it will mix so that it will go to this compressor. Then the compressor will compress until it reach the superheat region. Then it will be the superheat so that it can go to the condenser. Now, so compressor, condenser, expansion valve, evaporator, evaporator. Okay, so there's a combination of this mass flow, M4 and M7. So it will go here also to constitute the M1. No? So that is what we are talking about here. No, to be clear. So let me clear this up so that you can see in a clear. Look at this, yeah. So M1. So that is the mass entering the compressor or the combination of M4 and M7. What is M4 and M7? That those are mass flow rate of the evaporators concerned. No? So at the end of the evaporators, it will go to the compressor, suction at the entry. So all we have to do is M4, we get that 0.0319 here. Then M7 is here, 0.0648. We were able to get that now from the heat load of the second evaporator. So we were able to get the total of M1, right? So M1 is the one entering the evaporator. M1 is here also, no? M1, H1. And M1, H1 is the combination of these, again, of this energy balance, because mass times enthalpy is energy, no? It's in kilowatts, no? So mass 6, H6, and M8, H8. So let me illustrate that. I think I click here. So look at this, yeah. So here, so M8, there's a mass here, M8, mass 8, and H8. Then here, M6 and H6. No, so there's a junction. Look at this, and here, then this 7, so mass 7. Why do we need that? Because we are going to calculate for the refrigerating effect. Yeah, refrigerating effect later. So we need to have this mass of refrigerant entering to the evaporator. So let us immediately go back to this, right? So here, the heat load, no, at the evaporator, 10 degrees centigrade is MRE. Then the M, as I explained, as I explained, is M4. Now look at this, M4, the mass of refrigerant coming into evaporator 1, which is at 10 degrees centigrade, is this MRE. What are the enthalpies involved? You can see here H5 and H4. This one, H5, H4. Then the mass flow is M4. So it follows here, the formula is M4, H5, and H4. Now, the question is, do we have the heat load at the evaporator 1? Yes or no? Yes. Look at this. The problem says 35 kilowatts at 10 degrees centigrade. No? So the evaporator operating at 10 degrees centigrade has a load or heat load of 35 kilowatts, no? Or cooling load, meaning the amount of heat that it's going to absorb is 35 kilowatts. So here, if I may put here, no, so 35 kilowatts is given. M4, that is what we're going to find. H5 and H4, it's given now. H5 and H4 is given. We already got that, right? H5, here. We have H5, we have H4. Okay? So only we can find is the M4, mass flow at the entrance of the evaporator 1, which is at 10 degrees centigrade. So just plug in substituting values 35 kilowatt is just 35 kilojoule per second. Now we convert kilowatt into kilojoule per second so that we can cancel the other parameters or units. Now, so substituting values, immediately we have this M4. Okay, same is true. Same process we have to do in second, no? Second evaporator. The second evaporator is operating at a much lower temperature, which is, according to the problem, -5 degree centigrade. This one, at -5 degree centigrade, we were given a heat load, no, the amount of heat that the evaporator should, no, by design, absorb. No, it should absorb how many kilowatts? Let me go back to the problem so that we can see. At evaporator -5, it should have a 70 kilowatts load. No? So 70 kilowatts load. No? So all we have to do is to substitute 70 kilowatts here. This M7 is what? That's the mass flow rate entering the evaporator 2. Look at this. No? So let me clear this up. Okay. This is evaporator number 2. The entrance is 7. No? So our mass up appropriately, no, should be designated as M7. So this is the suction. This is the discharge at the saturated vapor, no? Discharge of the evaporator, which is the entrance of the compressor also. Okay? So going back to this, all we have to do is to plug in. We are going to find M7 at the second evaporator at the -5 degree centigrade. H8, we were able to get that because it is in the vapor line. And H7, we were able to get that because it is at the constant line. So look at this. So, yeah, H8 is the Hg at -5. No? Then we have, what's the other? The other is this one, H7. Huh? H8 minus H7 for evaporator 2. Do we have H7? Yes, here. No, because it's the same as H3 and H4 and H7. It's a constant enthalpy, no, because of the expansion valve. So all we have to do is to plug in. Easily we can get the M7. That is the mass entering, the mass flow rate of refrigerant entering the suction of the evaporator number 2, which is at -5. No? So we can get the M7, M4. Why do we need that? Because we will have the so-called mass balance according to first law of the thermodynamics, right? So mass entering, mass leaving, energy entering, energy leaving, energy in, energy out. First law of thermodynamics. So when you add M4 and M7, that is M1. So look at this, right? So look at this. Where is this? I think here, right? So here. So this, the mass 7, no? So the mass 7 is here. So the mass 7 is here, same mass, no? Law of conservation of mass, same mass here. That is the evaporator number 2. And then M4 is at evaporator number 1, no? So when you reach the end of the evaporator, so it will go to the compressor, right? According to our problem. So here is the evaporator. Let me just um, illustrate. So evaporator, this is the expansion valve. At a lower pressure, then evaporates. The liquid should evaporate because the compressor only needs a gaseous state. You cannot put a liquid in the compressor. It will explode. No, it will damage the crankcase and everything. No, it doesn't need a liquid here. Compressor needs gas or vapor only. So evaporator, after the evaporator, it will go to the compressor. And here, there's a meeting point of M4 and M7. Look at this. Now, M4 no, and M7. So let me illustrate that here in our diagram. No, so where is that? Here, M4. Look at the mass. No, the mass entering at the first evaporator is this. The mass entering at the second evaporator is this, no? Then it will mix so that it will go to this compressor. Then the compressor will compress until it reach the superheat region. Then it will be the superheat so that it can go to the condenser. No? So compressor, condenser, expansion valve, evaporator, evaporator. Okay? So there's a combination of this mass flow, M4 and M7. So it will go here also to constitute the M1. No? So that is what we are talking about here, no? To be clear. So let me clear this up so that you can see in a clear. Look at this, yeah. So M1, so that is the mass entering the compressor, or the combination of M4 and M7. What is M4 and M7? That those are mass flow rate of the evaporators concerned. No? So at the end of the evaporators, it will go to the compressor, suction at the entry. So all we have to do is M4, we get that 0.0319 here. Then M7 is here, 0.0648. We were able to get that now from the heat load of the second evaporator. So we were able to get the total of M1, right? So M1 is the one entering the evaporator. M1 is here also, no? M1, H1. And M1, H1 is the combination of these, again, of this energy balance, because mass times enthalpy is energy, no? It's in kilowatts, no? So mass 6, H6, and M8, H8. So let me illustrate that. I think I click here. So look at this, yeah. So here, so M8, there's a mass here, M8, mass 8, and H8. Then here, M6 and H6. No, so there's a junction. Look at this, and here, then it will go to the compressor port, compressor suction port. No, so if I may clear this, M8, enthalpy 8. This one, mass 6, enthalpy 6. Then it will go to M1, H1. This one, yeah? So it will go here. The involved here is M1 and H1. Do we have this? We have. No? We were able to compute already the M1, and then I think we have to find the H1 in the process. Yeah? But the M1 we already have, right? M1 we already have. No? So the mass balance is this, no? M1, H1, this one, no? That is the resultant, yeah? That's the meeting point. Resultant M1, H1 is coming from the components. What are the components? M6, H6. Another is M8, H8. Now, but M8 is also the M7. M8 is also the mass 7. So let me put that here. M8 is M7. Look at this, yeah? Here, the same, right? So the mass entering at the suction of the evaporator number 2 is the same, no? Law of conservation of mass, the same mass. Mass entering, mass leaving. So M7 is M8. So you want to get the M8, just copy the M7, right? So that is only our point, no? Where would you get the M8? That is the M7 coming from the entrance of the evaporator number 2, no? So this is the equation. All we have to do is to plug in the values, no? So we have to plug in the values. If we plug in the values, we can get the other parameters like the M4, no? Because here we have the refrigerating effect at 10 degrees centigrade, which is the middle evaporator, or evaporator number 1. So M4, we don't have M4, but we have H5 minus H4. How do we get H5 and H4? Look at this, yeah? H5, saturated vapor. H4, saturated liquid. Coming from saturated liquid, 3. 3 is equal to 4 in terms of enthalpy. Look at this. 3 is is to 4, no? And in enthalpy of 3 is equal to 4, and the other enthalpy involved is H5. So we have already H5, which is the enthalpy of gas. So easily we can get the mass, no? Because we have to plug in only, right? So we have the heat load at the evaporator 1. We have H5, we have H4. Easily we can get the M4, right? So M4 is this. So that is the way to do it, no, by calculating the refrigerating effect at the first evaporator. Now we can also get the other M at the evaporator number 2. Look at this. Now, do we have a heat load? Yes. No, because at negative 5 we have a 70, right here, 70 load. No? I think this is kilojoule per second, no, kilowatt. Yeah, M7 equals H8 minus H7. Now this is the refrigerating effect, no? H8 minus H7. So H8 we have now because it's the enthalpy of gas, and H7 is enthalpy of fluid. Let me put the background here. Now look at this. Let me clear this so that it will be a lot clearer. So the refrigerating effect at this evaporator is evaporator number 2, which is negative 5 degrees centigrade. Is the saturation temperature. We can get the enthalpy of gas at 8. We can get here the enthalpy. So H8 and H7 we have because H7 is just the same as H4 and is also the same as H3. So easily we can get the H8 and H7 multiplied by the mass 7. We already computed that a while ago. So we can have that refrigerating effect. But the heat load is already given at that point, right? So 70. Look at this, no? QE is 70, M7 is unknown, H8 and H7 is what we're going to find. No? So substituting values, M7 equals QE at negative 5 over H8 minus H7. So this is this, right? H8 minus S7, then this the heat, no? Heat load, 70, no? So 70 uh, 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 values. Now, so easily we can have the M7. So now the equation a while ago is this, right? So this one, M1H1 equals M6H6 plus M8H8, but M8 equals M7. So if we substitute values, then we can get the the values. Yeah, so we can get easily the H1. No, so because we don't have H1, no, because we need that mass 1 equals M2 H2 minus H1. No, for the work of compressor, mass 1 we have H2 and H1. H2 we have, no, because it's a superheat, but H1 we don't have. So H1 we were able to get H1 because of the energy balance, mass and energy balance. Okay, yeah, so we were able to get H1 here, right? But H2 we were able to get because it's a superheat here. Look at this. Yeah, so here this so there's a superheat region. This constant. Look at this, the constant. Yeah, so constant enthalpy, constant entropy, S equals C. Then we have this pressure. What is our pressure here? There's a condensing pressure here, right? There's a condensing pressure here, so we can get from the table the enthalpy H2. So all we have to do, because everything is complete now, we can get the power. The power of the compressor or the work of compressor is mass flow, which is 0.0967. We were able to get that in the energy balance. Then H2 here is the enthalpy. Then H1 by energy balance, no? H1 we were able to get the 1461. So H2 minus H1, 1665 minus 1461. Look at this, 1665 minus 1461.3, then times the mass 1, mass M at the suction of the 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 compressor. We were able to get mass 1, no? During the energy balance. No? Look at this. No? So mass 1 is just the M4 plus M7. We were able to get the M4 and M7 because they are the ones coming into the suction of the compressor. So we have the M1. All we have to do is to multiply M1 with the difference of H2 and H1 to get the power. So the work of compression is here. No? Work is only happening in compressor, no? The equipment that does the work, no, yung trabaho, no, pinipipi yung refrigerant, gumagawa niyan ay compressor. It's the compressor. So power is this. We don't have efficiency, so it is assumed 100% efficiency, no? So it's just this. If there's an efficiency, we could multiply that. Yeah? So here we have the power of the compressor or compression. So COP, coefficient of performance, is only the refrigerating effect divided by the power or work of compression. So refrigerating effect over work of compression. So what are the refrigerating effects? We have two, evaporator 1 and evaporator 2. We have this, yeah, 35 kilowatts plus 70. Those are the heat load of, or the refrigerating effect of the evaporators concerned, and the work of compression is the one that we just calculated using the energy balance. So the work of compression is this. So here 19.97 kilowatts. So here is 35 kilowatts. Then here is 70 kilowatts. Here is 19.7 kilowatts. So you just add this, divide. We have coefficient of performance, which is 5.33, which is good, no, excellent, no, because more than 4, no, greater than 4 is good, no. So coefficient of performance is 5.33, and the power is 19.7, or the work of compression. Again, I think that's all for now. We were able to get. We will continue later with the other problems. We have one or two more couple of problems that we are going to discuss in the next meeting. So I think that's all for now. Thank you very much for listening. I guess I have to say apology because we extend like 5 to 10 minutes.